Our next lesson here in this unit is going to be graphing and motion. And in this unit, we're going to look at three things. We're going to look at basic graphical analysis of motion, that is looking at distance or displacement, velocity, and acceleration in terms of graphs of these things and how to convert between them just using graphs. And we'll look at basically three parts of this. One is motion from velocity versus time graphs. The second is motion from acceleration versus time graphs. And the third is motion from distance versus time graphs. How to find velocity, acceleration, distance from those three things. So let's talk about a little bit what we're going to be doing here. So this refers back to a little of what we did in the last unit. So we said, remember that if we are given a distance, velocity, or acceleration versus time graph, or a function of these things, we can determine, that shouldn't be determining, that should just be determine, we can determine the other two motion functions by finding either the slope of or the area under the graph. And so we had this nice little illustration here that if we started with a distance versus time graph and we wanted to find a velocity versus time graph, if we find the slope of a distance versus time graph, that will give us the velocity versus time graph. Now, if we have a velocity versus time graph, if we were to take the slope of that, that would give us the acceleration versus time graph. But if we wanted to find the distance versus time graph, from our velocity versus time graph, we'd have to take the area underneath our velocity versus time graph, and that will give us the distance versus time graph. And that's basically what we have right here. So in general, if we're given the graphical representation of a distance versus time, a velocity versus time, or acceleration versus time graph, we can then use that to create graphs of the other two functions, either by finding the slope if we're moving to the left or to the right, or by finding the area underneath that graph moving to the left. And we can use those to determine the values at any time. So let's go ahead and take a look at how this might work. Here we have basically a graph of velocity versus time. So we have velocity going to be on this axis going up here. We have time on this axis going this way right here. And we have just a series of points that are nicely drawn out on here that show us basically where we have here. Now, first thing we sort of want to do here is we could say, let's just figure out some basic stuff about this. This is a velocity versus time graph. We have some questions over on the right. It says, first thing, the velocity. What is the velocity at 5 seconds is our first question here. Well, for this, all you have to do is you just have to look at what happens at 5 seconds. So 5 seconds is sort of right in here. And so we follow that up. And we follow it up, we're going to find basically it's this point right here. And that point is somewhere halfway between 4 and 5. In fact, it's right on that line, halfway between 4 and 5, right in there. And so we'd say it'd be at 4.5, in this case, meters per second. Pretty straightforward there. Just read it off the graph. 20 seconds? Well, 20 seconds is down here. And so that one, we'd have to follow this back all the way across, and it looks like it's at negative 3.5. And so at 20 seconds, it's negative 3.5 meters per second. And so to find velocity on a velocity versus time graph is basically trivial. All you have to do is just set it up, take a look at it, and that's it. I'm going to get rid of these for a second because we're going to need to do some drawing on this to figure things out. So, the next question. Acceleration. What's the acceleration at some point? Well, remember we said before is that the acceleration of a function is simply the slope of that function. Acceleration of a velocity versus time graph is simply the slope of the curve. And so, really looking at this, we sort of have several sections here. We have one section which goes up like this. It's our first section. A second section that goes over like this. A third section that goes down to here. Then it sort of has a kink in it, goes like this, and then another section that goes like that. And so we can divide this into 1, 2, 3, 4, 5 different sections here. To find the acceleration, we just need the slope of those sections. On the first section, over on our far left, it starts at 0 and ends at 4.5. So it has a rise of 4.5, and then it takes 3 seconds to do that. And so the rise is 4.5 divided by the run, which is 3. And so we get, basically, this has a slope of 1.5. right through there. And so the acceleration on that first section is going to be 1.5. The units would be its rise over run. The rise is meters per second. The run is in seconds. And so meters per second divided by seconds is meters per second squared. And that's, of course, an acceleration, just like we'd expect here. On the second section here, the rise is 0. It's a level section. Since the slope is 0, the rise is 0, it means the slope is 0. And so the acceleration over here is going to be 0 meters per second squared, right there. On our next section, from 7 seconds all the way down to 13 seconds down here, if you can read that, basically it drops from 4.5 all the way down to, see this point right here, going across looks like negative 1.5 if we sort of follow that over here. And so we would say to find our rise, it would be the final one, negative 1.5, minus the original one here, which is, we said 4.5. So we get a rise of negative 6 divided by a run. We started this off at 7 seconds. We ended it at 13 seconds. And so 7 to 13 is 6 seconds. So we divide that out. So we said negative 6 divided by 6. So this right here has a slope of negative 1. And so the acceleration on that section is negative 1 meter per second. On our fourth section down here, it starts at negative 1.5 and it ends at, follow that over all the way, at negative 3.5. And so negative 1.5, negative 3.5, that's a rise of negative 2. The run goes from 13 seconds down to 17 seconds. That's 4 seconds. So we'd say negative 2 divided by 4. And doing that, you get negative 1/2. And so 0.5, that is a 5, meters per second is what we get for the slope of that section. So that's the acceleration of the whatever our object is. We don't know what it is, just an object. And then our last section down here, we're basically told that, we're looking at it, it's not rising again. And so it's going to have a slope of 0. And so the acceleration is back to 0 again, meters per second squared. And so that's basically what we've got for these sections. The question is, what's the acceleration at 5 seconds? Well, 5 seconds right here. We sort of follow that up. We can see very clearly that the slope at that point is 0. And so the acceleration is 0 meters per second squared. At 20 seconds, right over here, follow that down. Look at what's happened here. Once again, the acceleration is 0 meters per second squared. It's a flat slope in both cases. And so that's what we end up with here. So if we have a velocity versus time graph, you want to find the acceleration, all you do is look at the slopes. Now, our next one here, last one, is going to be distance. So let's take a look at distance here. We'll clear things out once again so we can start over on this. To find distance, that would be moving to the left on our other one. Is, moving to the right to find acceleration. It's sort of on the table that we had on the previous slide, where we sort of had that. You use slope. But to move the other direction, to go from velocity to distance, you have to find the area underneath something. And so we basically are going to need to, in the first case, we're looking for what happens at 5 seconds. So 5 seconds is sort of our question here. And I'm a little bit not functioning here, so just a second. So our next one here is looking at distance, and so we have 5 seconds as our first one, and so 5 seconds right down here, that's going to be this point. And so what we want to look at is we want to look at the area underneath the curve at 5 seconds. Now that area underneath the curve would basically be, if we were to basically once again sort of plot out our path here at 5 seconds, we've sort of got a little dotted line that works this way, and so we've got that one here, and we've got our axis is our other line, if you can sort of see that axis going along there. I couldn't really show up very well. So that's our axis right here. This basically marks out an area in between this graph here. What we need to do is we need to find what is that area. And to find that area, what we're going to want to do is we're going to want to break this, since this is not a regular shape, into 2 parts. We're going to have one part that's going to come down here, if that's visible at all. So sort of a green triangle down here. The other part is basically going to be a rectangle. That's a little more visible. So we have a rectangle here and a triangle right there. And we want to find out what are the areas of this section here. So for the first triangle is that it has a base of 3 down here. It has a height of 4.5. And so we'd go ahead and just basically use our triangle formula, 1/2 base times height. So 1/2 times 3 times 4.5 gives us an area of 6.75. And so I'll just sort of draw down here, 6.75. Now, note that to do this, we're taking base, which is time in seconds, times height, which is in meters per second. So seconds times meters per second is basically going to give us basically meters, which is a unit of distance, which is what we want it to be. So we're right on that one. So that's 6.75 meters. This section right down in here would have to have, it's got a length of 2 seconds and a height of 4.5. And so we'd basically say 2 times 4.5 is 9. And so that has an area of 9 meters that's in it. And so our total area that's been traveled, total distance, that's been traveled so far would be 6.75 meters plus 9 meters. And so 15.75 meters. And so 15.75 is what I get for that one. All right, so I got that just fine. The next one is 20 seconds. And so let's erase what we've got here. Let's look at what happens to going to 20 seconds. So looking towards 20 seconds here, we've got a little farther path. It's going to first come up like this, then go over, then down to our little kink, zip over this way, and then all the way to here. We've got to find basically this whole area that's between that and our axis. So let's set this up. First section is this sort of this first little quadrilateral that we have here. We're going to break this into 2 triangles and a rectangle. Down here, we're going to have to break this into one little triangle here. We're going to break it into a rectangle, which is off to 17 down here, a triangle down there, and a rectangle. And so lots of little pieces here to figure out, but we can figure out what they are here. On the first one, this one actually I think we already figured out. This one was the 6.75, I believe, because it had a length of 3 times 4.5. So when we did that, yeah, we got to think about 6.75. And so 6.75 is the area of that section right here. Our next section is a little longer than the last one. In this case, it goes all the way from 3 to 7. So it's 4 long and then 4.5 tie, because this comes over to 4.5 right here. And so 4 times 4.5 gives an area of 18 meters. I notice this sounds weird. We're talking about areas in meters, but basically that's what we get when we're talking about, figuring out the area underneath this graph here. We know it has to be in meters based on the units. And so you sort of have to go with the flow on that a little bit, is that just the space we're in right now, where we have a distance in meters per second, a time in seconds, you end up getting an area that's in meters. But right now, that's all we have here, is that the area underneath the velocity versus time graph is a distance. So let's keep going here. Our next section on here basically goes from 7 seconds down to, well, what exactly happens here? It's sort of hard to tell where this crosses. It crosses somewhere between 11 and 12. Looking at this very, very carefully, if we look at this point right here and this point right here, we can see that that it goes down by 1/2 from here to here and up by 1/2 from here to here. That means it's going to cross right in the middle. So it's going to cross, technically, if my drawing was straight, this would cross right at 11.5 seconds. So oftentimes when you're doing this, you're going to have to look very, very carefully. Sometimes you may even have to calculate to see where it's going to cross an axis, to see how far your length is going to be here. But either way, this one goes from 7 to 11.5, and so that's going to be basically 4.5 seconds long, times the height, which is also 4.5, and then once we've got that times 1/2, because it's a triangle, and so 10.125 is what the area of this one is. Now, let's look at our next little triangle. Our next little triangle is down in here. Now, for that one is 1.5 long, because it started at 11.5 and ends at 13. And the height here, let's see if we can follow what this is over here. Looks like 1.5, or negative 1.5, technically, because it goes down. So we'd say negative 1.5 times 1.5, because that's the number of seconds long it is from here to here, times 0.5. And so in doing that, so times 0.5, I just messed up on my calculation, so 0.5 times 1.5 times negative 1.5. So I get negative 1.125. Now, look at what we've sort of got here. We got a negative sign here. The reason why is that whenever you're basically taking areas on graphs, if the area falls below the axis, it's considered to have a negative area for the purposes we're doing here. Now, if you think about this sort of makes sense. Whenever the graph is below the axis, that means the velocity is negative, which means it's moving sort of backwards. And if you're moving backwards, that means your distance is going to become, or your displacement technically, is going to become more negative. And so that sort of makes sense here. But all we need to know for right now is that whenever you basically look at a graph that goes underneath the axis and you find an area there, those areas underneath the axis are negative. So that's what we've got here. So negative 1.125 for that area. Our next little section, we have this little box, a little rectangle right here, which goes from 13 to 17, so it's 4 seconds. And we said before that it goes down to negative 1.5 is the location of that point right there. And so it would be 4 times negative 1.5, and so we get negative 6 for that area right there. Our triangle is next. It goes from negative 1.5 all the way to basically this point right here, if I can sort of draw that across, negative 3.5. And so we go from negative 1.5 to negative 3.5. And so that's going to be a difference of negative 2. And so it'd be negative 2 times the length, which is still 4 seconds, 13 to 17. So times 4 seconds times 1/2. And so we get -4 for the meters for the area of that. And then to get to 20 seconds, we have to get our final sections. This last little rectangle right here goes from 17 to 20 seconds, so it's 3 seconds wide. It is, we said before, -3.5 long. So -3.5 times 3 seconds. So we get -10.5. Okay? And so to find our total distance that is traveled here, we want to add all these areas up. So 6.75 plus 18 plus 10.125 minus, because we're subtracting here, 1.125, minus 6, minus 4, and then minus 10.5. And in doing so, I get 13.25. So 13.25 would basically be what we have for meters. Meters is the distance or the displacement this object has at 20 seconds. So we go through a lot of steps there, but that's basically how it sets up. Our last question is simply one of maxima. What is the maximum velocity? What is the maximum acceleration? What is the maximum distance? So for maximum velocity, it's pretty straightforward. You look on the graph, what's the highest point? In this case right here, the maximum velocity is basically going to be this section right up top. That's where it's at its fastest, and so that would be at basically 4.5 meters per second. Pretty straightforward on that. Maximum acceleration, since acceleration is slope, you're looking for the place where the slope is highest. In this case, there's only really one point where the slope is positive. That's going to be this section right here. And we found before the slope of this section is 1.5 meters per second squared. And so our maximum acceleration would be negative. It would be 1.5 meters per second squared. Once again, pretty straightforward here. Maximum distance, though, this one may take a little more work. We've got to find where it's gone the farthest. But if you think about this, if you look at what happens here, for the first section of this graph, for the first 11.5 seconds, this object is moving forward. But then for the next, what is that? That's 20 to 12, so it's 8.5 seconds. Basically, the object's moving backwards. And so we would expect that the point where it's basically going to be at its farthest distance is going to be the point where this transitions, where it crosses over, right about in here. And so the maximum distance will be whatever distance it has at that point, because it's only been moving positive before that. It's only moving negative afterwards. And so it would be 6.75 plus 18 plus 10.25. And so 6.75 plus 18 plus 10.125. And so the maximum distance here is 34.875. So our maximum distance, 34.875 meters right there. And that's how you go about using a velocity versus time graph to find acceleration, distance, and velocity, including their maxima there. So that's velocity versus time. What do we do if we don't have velocity versus time? We have a different type of graph. Let's take a look at acceleration in this case. The basic process works exactly the same. The only difference is that we sort of have to take two steps. If we have an acceleration versus time, that basically what we're going to want to do here is to go to velocity, we've got to find the area. But then we basically, to get to distance, we'd have to find sort of the area under that. And so really what we're going to do here is we are going to use our existing graph of acceleration to create a graph of velocity that then we can basically do some math on. We can find that the areas are. So let's look at this first question. First question is, what's the acceleration at 5 seconds? Well, 5 seconds, all we have to do is just go and say, okay, we're at 5 seconds again. At 5 seconds, basically is going to be right here. And so at 5 seconds here, we basically are at a acceleration of 4.5 meters per second squared. Note that we have, since this axis is now acceleration over here, since this is acceleration versus time graph, for the black part, we'll get to the velocity part a little bit later here. We have units of meters per second squared. And so therefore at 5 seconds, the acceleration is 4.5 meters per second squared. That's all we're reading here. 20 seconds, that's this point right here. We sort of follow it back over, and it's -3.5. And so at 20 seconds, it's -3.5 meters per second squared would be our acceleration right there. Pretty straightforward. So we got that. Next one up would be velocity. To find the velocity at 5 seconds, we would basically need to find the area at 5 seconds. Now, here is sort of where we start getting a little bit interesting. We could just go ahead and find the area at that point, the same as what we did last time. Basically, we say we're at 5 seconds, so it's this point right here. And so what we're going to do is we're going to create a graph that works a little bit like this. sort of do it out here, divide it into two sections. Find the area is the same as what we did last time. We've got an area of a triangle. We've got an area of a rectangle here. And that will work just fine. If you do that, you'll be completely right. What we're going to do here instead, though, is we're basically going to try to create a velocity versus time graph from our acceleration here. That way, we won't just be able to get just the values at 5 seconds and 20 seconds. We'll be able to get the values at any point. And furthermore, once we've got that graph, we're going to be able to find the distance by looking at the area underneath that graph, that velocity versus time graph. And so we're going to clear this out a little bit, and we're going to sort of see how this works. So the first thing that we basically know here is that this object is going to have increasing velocity for its first section. And so let's take a look at sort of what happens there. Turns out I had the wrong graph up here. That's the reason why I was getting a little perplexed here. But let's take a look at what we've got right here. So this is actually the acceleration versus time graph that we've got. We still have acceleration along this axis. Going up this way, we still have time along this axis. If we want to find the acceleration at 5 seconds, that value would be right here. Basically what we do is we do the same thing we did before, is that basically you're going to set up, you know, so we have our function that goes along here. You're going to go from 5 seconds, 0. You basically have this little box is going to be the area. If you find that area, then that tells you what the acceleration is at 5 seconds. That's sort of the simple way to do it here. In this case, it's 4.5 high by 5 wide. And so if you wanted to figure out what the area of this box was, you simply take 4.5 times 5. And so when you do that, you get 22.5. And so 22.5 is what we get for the velocity at this point. 22.5 right there. So that's how you get that. If you wanted to get it at 20 seconds, then basically you have several boxes here. We have, this is our function right here. Now note this is a discontinuous function. This object basically starts off with a fairly high acceleration, 4.5, right about in here. Then all of a sudden it basically drops down, now has a lower acceleration at 1.5 in this section right here. Then all of a sudden starts decelerating. Has a brief deceleration right in here of negative 1.5. Then actually, I forgot a section right here. Yeah, then it actually basically doesn't decelerate for a while. It's basically just coasting. No acceleration or deceleration. And then finally, a very negative deceleration at about 3.5, negative 3.5 at the very end here. So if we wanted to find the velocity at the very end, what we want to do is we want to break this into, once again, sections here. The axis is one of our sections. The function is the other one. So I have a box right there. I have a box right here. I have a box right here. I technically have a box right here, but it's basically a 0 box. Sorry, that goes all the way back to here, actually. So it's actually a 0 box right in there. And then I have my final one right down, that's not a very good drawing, right down here, which is my last area. And so I'm looking to find basically what are the areas in here if I want to find what velocity it has at 20 seconds. So in this case right here is that we do technically need to know what the original velocity was. These are actually the difference between the velocity originally and the final velocity. If we assume that it starts off at 0 is the original velocity, this would tell us what the final velocity is in that case. But so looking this out, we have that this first box up here on your far left is 4.5 by 8. And so 4.5 times 8 gives you 36. 36, since we have basically meters per second times seconds, our unit's going to be meters per second squared times seconds. We have meters per second, so it is a velocity right there. So that's the area of this first box here defined. So that would tell you that after 8 seconds, this thing is going to be going 36 meters per second. Now, next section here goes from 8 to 12. That's 4 by, trace it back, it's going to be right over in here, so that's 1.5. So 4 times 1.5 gives you 6. So this is going to be 6 meters per second right in there. And that's what we have for this. So we have 6 meters per second right there. Now for our next box right here is on the negative sides of things. And so basically, let's see, if it's negative right here, then we would say that it is, let's see, if I trace that over, all the way over here, that's at negative 1.5. And so it's negative 1.5 times, looks like 2 seconds here. So times 2 seconds, so we get 3. So this right in here is 3 meters per second. The next section right here, well, it's going to be 0 because this is not it shows an acceleration of 0 during this time. And so the change in velocity is basically 0 during this point in time. So it's only 0 change in velocity between 14 and 17. And then for our last section here, we have go from 17 up to 20. So we have 3 seconds that goes along right in there. And then times follow this back line over here. It's at 3.5, negative 3.5. And actually that is negative 3 back there. I forgot to put a negative sign on that. So we have 3.5 times 3. So we get negative 10.5. That's 0.5 right there. So this basically right here tells us what this is at 20. And so if I wanted to find the velocity at 20 seconds, I'd say 36 plus 6 plus negative 3, then plus negative 10.5. Zeros in there too technically, so 28.5. And so I get for my velocity at 20 seconds is 28.5 meters per second. And so that's what we got here. Because it accelerated a lot positive, but not a whole lot negative. It didn't decelerate all that much. So this, we now can find our accelerations. We can find our velocities. Acceleration, just read the graph. You find your velocity, basically find the areas. But what about the distances? What about the distances? Well, to find distance, what we're going to want to do here is we're going to want to regraph this. We're going to take the data that we have right now that's on the screen that we know that in the first section, the first 8 seconds, it goes from 0 meters per second all the way up to 36 meters per second. The second section, it goes from 8 meters per second to 6 meters per second, and so on and so forth. We can use that to basically find where this object's going to be. That's one way to look at this. The next way to look at this, to find basically to create our velocity graph, is to know that the slope of the velocity graph is the acceleration. And so if you look at this section right here, for the first piece that's right up here, sort of our first right here, this little section right there, that the value of the acceleration is 3.5 the whole time, which would mean the slope of the line is 3.5. Now, if you think about it, this data right here, the fact that we know it's going to end up at 36 after 8 seconds, the fact that it's got a slope of 3.5, this should give us enough information to figure out how to set up this second graph. And so let's see what we can do with that. And so I'm going to put our points in here. So we know to start off with, and we're now going to do basically our velocity graph. See, we have velocity over here. We're going to do this next. And so our first point right here is basically the original velocity is just at 0. And so that's our point right there. So we're going to put a point right for that one here. Now, the next thing that we know is that after 8 seconds, it has a distance of 36. So we sort of need a scale over here on the right. We don't have a scale right now. We know this right here is going to be 0, but we don't know a whole lot more than that. To find our scale, we sort of need to know what our maximum or minimum is. Just looking at our distances here, or sorry, at our velocities here, the areas we came up with, we can see that this gets up to positive 42, 36 plus 6 right here. And if we add those two up, we get 42. Then it starts going backwards after that. So we know it's going to be at a maximum of 36. Since the final velocity was 28.5, we know it's never quite going to get negative. And so we know that our top piece right up here has to be at least up to 36. Now, we can see up here our maximum scale we've got up here is 8 right now. Fortunately, if you take 36 and divide by 8, you get 4.5. And so, let's see. So our best bet here, since we have 8 times 4 boxes per one, 32 boxes going up here. Let's see. So we have 32 boxes up to this point right here. We need to get up to 42. So our best bet is probably going to be that every box is going to be 2 meters per second. So every 4 boxes would be 8 meters per second. So if I were to sort of draw this out, this right here would be 8 meters per second, another 4 boxes up. I'm going to try to count this out right, if I can do this right. So there's a mark right here. Go another 4 boxes up is right here. Another 4 boxes up right here. Here. So 8, 16, 24, 32, 40, 48, 56. And then next one would be 64 right up there. And so this is going to be our scale in meters per second. Since this object never drops into the negative, we don't have to worry about having a negative down there. So we know it started off at 0. We know that after 8 seconds, it's now basically at 36 meters per second. So 36 is halfway between 32 and 40. And so that's going to be, Looks like it turns out to be right about here, actually. That was sort of an interesting coincidence. Ended up at the same point here. So we know it's going to end up at that point to be right here on our new scale, the scale that's on our right. Not the scale that's on our left, because this right scale is our velocity scale. And so we know it starts off at 0. It ends up at 36 meters per second. Now on our actual graph that fits in between that, well, what we know, as we said, is the acceleration was constant. It wasn't changing. And if the acceleration is constant, it wasn't changing. That means the slope of the velocity of the time graph is constant, not changing. That means it's going to be a straight line. And so we can go ahead and draw up a straight line for that section right here on our velocity versus time curve, which is what we're creating right here. On the next section, we know that it accelerates by 6 meters per second squared, it has 6 meters per second squared is what is the increase in our velocity. So it starts off at 36. By the time it reaches 12 seconds, it's now at 42. 42 is basically going to be, since each box is 2, so at 12 seconds, we go up here, would basically be right about, if I can get the right spot here, right about in here, if I'm doing my math right, if I'm following this properly here. And so in this case right here, we have sort of a kink, and it's going to go up this way. That should be more of a straight line there. And so for this one right here, we can basically say the graph's going to look like this, because once again, if we look at the slope between 8 seconds and 12 seconds, we can see, or we basically can see the acceleration is constant between 8 and 12 seconds. It's always at it's always at 1.5 meters per second squared. And so since the acceleration is constant, that means the slope would be constant. That means it has to be a straight line still. And so this is what we have so far. This gets us up to 11 seconds. Now, over the next section, it basically goes down by 3. And so we're now at 39 is basically the value we have at, what would that be, 12, 13, 14 seconds. And so if we're at 39, that's going to put us basically right about in here. And so the next section would be basically a line that goes like that, because once again, we have constant accelerations, which means constant slope. It will be a negative slope, of course, goes downward because of the fact the acceleration is negative for this section right down here. So that sort of makes sense. For our next section, between 14 seconds and 17 seconds, there's no change. It's at 39, it's going to stay at 39. And so basically at this time right here, we're still going to end up right about there, that we have 0 acceleration for this section, so we'd expect 0 slope. And so as a result, we have a 0 slope section right here. It's basically flat. For our last section here, we know it drops by 10.5. So it started off at 39. Now it's going down to minus 10.5 is 28.5. So 28.5 is going to be right about in here. So our last section is going to go down like that. This black graph that I've just created is our velocity versus time graph. We're able to create one basically just right off of this. Now that we've got our velocity versus time graph, we can go ahead and basically say, well, let's find what our distances are. At 5 seconds, that's basically going to be this spot right here. And so we're basically going to find what the area is underneath that black graph right there. And so we'd have to say, okay, well, first thing, where is it at 5 seconds? How high is it here? Well, the point on that graph is going to be basically whatever area we would have gotten at 5 seconds here. That would tell us how high it is, what value sort of along our velocity axis right over here it would have. And so since we said before on this, I think we wrote it down previously, but I don't have it up on the screen anymore. So it was 5 seconds by 5 seconds by 4.5. And so we had 22.5 is what we had for the velocity on this one. And so at a distance of 5 seconds, this right here, this point should be at 22.5. I don't know if it shows up on the screen at 22.5, but that should be at 22.5. I drew it properly here. And so we know it has a height of 22.5. It has a length of 5. It's a triangle. So 0.5 times 22.5, because that's going to be what this height is, this length right here. Times basically the time across here, which is 5 seconds. And so in doing that, we get 56.25. So at 5 seconds, it's traveled 56.25 meters right there. 20 seconds. If we want to find what was at 20 seconds, we need to find this whole area here. To find the whole area, we basically got several sections. We have a triangle section that sort of makes up this part right here from the beginning all the way back over here. We have basically this section right here, which we have basically a rectangle that goes around here and a triangle here. We have a little triangle right there, a rectangle that goes right here, another rectangle right there, and then a triangle and a rectangle here that goes below it. Now, do we really need to figure out all these areas to show you how we do this here? Not really, but you can see it's quite doable. Is if we wanted to figure out this first one here, we know that this one right up here at the very top, right up there, ended at 36. And so if we wanted to find the area of this big triangle right up here, we'd basically say, you know, it has a length of 8. It has basically a height of 36 meters per second, and then times 1/2 to get it into this. So we get 144 meters for this section right here. For this section that's right up here, we know that it's basically 36 high across for this little rectangle. It's 36 by 8 to 12 by 4. So 36 times 4 gives us also 144 meters for that section here. For this little triangle right here, we know that it basically is from 8 to 12, so it's 4 seconds wide, times basically the height. Remember that this goes up by 6 is the rise that goes on, but basically from here to here. And so since that's rise is 6, we'd say times 6. So 4 times 6 times 0.5 because it's a triangle. And we get this is 12 meters for that. For this section right in here, we know that basically this rectangle is going to be what it is at the end of this section right here, which is going to be at 30. So this section right up in here, which that's at 39. And so it drops from 42 to 39. And so that's a drop of -3 times the length across right here, which is going to be 2 seconds. Since it's a triangle, times 1/2 gives us -3 is what we get for this piece right here. So -3 meters. We've actually saw it was the triangle right here. I never figured out what this other one was, this rectangle here. So for the rectangle, we said that we were at 39, and so this is 39 high, as we said, and so this is 39 across here times 2 seconds. And so 39 times 2 seconds is 78 meters for that section right here. This section that is right up here, that part of the graph right there, is also 39 high by 4 wide. So we'd say 39 times 4 since it is a rectangle, so 156 meters. So we get for that. For 2 last little sections here. The first one is this section right up here. We know it's at 28.5 high. That's what we found is the height of this one right here. So that's this length along in there. So we say 28.5 times 3 seconds, which is the time across here. So we'd say 3 seconds times 28.5 gives us 85.5. So we get for that distance in meters once again. And our last bit here would be this little triangle right here to find the area of that. So that triangle right here drops from 39 down to 28.5. That's a drop right here along this axis, -10.5. So we'd say -10.5 times the number of seconds, which is 3 seconds, times 1/2, so that's a triangle. So we end up getting 15.75. 75, it'll fit right in here. So if we wanted to find our total area, we just want to add all these up. So 144 plus 144 plus 12 plus, let's see, 78 for this section right here, plus 3 for the section above it, plus 156 for the section to its right, plus our last 2 sections, 85.5 plus 15.75. Now note that none of these were negative. The reason why is because if you look at these, they're all on top of the graph, that we shouldn't have any negative areas because it never drops below the graph here. And so my final answer here I get is 638.25 meters would be the distance that this object would have traveled based on our original acceleration graph. So we were basically able to get the distance off of this whole thing just by working backwards and working through sort of a graph. Find our velocity graph first from our acceleration graph. Then once we have the velocity graph, we can use that to find the next bit here. So last question is maxima. To find the maximum acceleration, just read the graph. Where is the graph the highest? In this case, it's the very beginning, that first section right along in here from 1 through 8 seconds, right along in there. That section has an acceleration of 4.5 meters per second squared. That's your maximum right there. So read the graph. For velocity, well, we create a velocity curve. That's our black curve on here. And so on the velocity curve, the highest point on that is this point right here, where we said we found out that the speed is 42 meters per second. So our maximum on that is going to be 42 meters per second. For our distance, the maximum, well, in this case, this thing's always moving in a positive direction. And since it's always moving in a positive direction, it's always getting farther and farther away from its origin. And we found at the very end at 20 seconds, it had a distance of 638.25. So we found this last section right here. So that's going to be the maximum one at 2. If the distance graph had ended up going negative, then basically the maximum would have been whatever distance whenever it crossed the axis and started going negative. Now, if by some chance what had happened was that it were to go negative, then go back positive again, you'd have to look at basically how much of the graph was negative, how much negative distance it went, how far backwards it went, and then how far forward it went again afterwards. And sort of look at each point it crosses the axis, find the distances at those points, and then find the distance at the very end, and see which one's the largest. So that would basically be the path that you would take here. So our very last section on this, I know it's a little complex here, is to basically look at a distance versus time graph. And so for our distance versus time graph, here's basically what we're going to do here. On this one here, it looks sort of a little bit different than one of our previous ones, because if you were to sort of sketch this, you can sort of see that we have a nice little flat section for the first bit. Then it's going to go down to this point right here. It kinks, goes down to here. But then we have a curve. We haven't seen any of those before. In this case right here, that's a nice parabola. So first question here would be, I've got it says acceleration. Let's find the distance first. This is the one that's going to be easiest to find. So at 5 seconds, what's the distance? Well, we once again go up and just read what this is right here. It's going to be 3 meters. So the distance at 5 seconds is 3 meters because our unit over here is in meters. At 20 seconds, we look up here. That's this spot right here. Follow it back over. It looks like it's going to be at 6.5. And so our distance at 20 seconds is 6.5 meters. All right. So pretty straightforward there. Next thing we want to find is velocity. To find a velocity, we want to find the slope. And so let's look at the section over here at 5 seconds. That's going to be basically what our slope is right here. And so to find that, we'd say, all right, it started off at 3 seconds at 4. It ended up, when it basically hit its kink, the kink was right here. At 7 seconds, it appears to be at 2. And so the rise was negative 2 because it went from 4 to 2. And so the rise is negative 2. The run, in this case, goes from 3 seconds to 7 seconds is 4. So we'd say negative 2 divided by 4. And so we're going to end up here with negative 1/2. And then so the velocity at 5 seconds is negative 0.5 meters per second. Didn't fit very well. At 20 seconds, well, this one's a little more difficult because it's on a curve. Well, basically what you'd want to do is you'd want to look at one of the adjacent sections to it. That's going to be an approximation. To actually find what it was, to actually find the real value of the velocity here, to find the precise value, you'd have to basically find what the slope of this, you'd have to find what the function is here, what the equation of this parabola is. If you have the equation of the parabola, you could then use calculus techniques to find it. But for what we're going to do here, we're simply going to say, let's look at the last 2 points along in here. And so for those, it started off, looks like at 3.5 over here, ended up at, I think that's 6.5. And so the rise here from 3.5 to 6.5 was 3 divided by the run, which is 1 second. And so we get basically an approximation here is going to be 3. And so we basically get that this is going to be 3 meters per second is going to be what we have right here. Now, this gives velocity. But to get acceleration, which is our last one, what we're looking for, we basically have to take the slopes of the slopes. And so to do that, we're going to sort of do the same type of thing we did before here. We're going to redraw another graph onto here that shows us where we're going to sort of start here. So to start off with, we have an acceleration of 0. Sorry, velocity of 0. That's what we start with. And let's take a look at what we have here. So for the first section, we ask, what is the slope of this first section right in here? Well, slope is 0. Boop. Which means that basically if the slope's 0, that means the velocity is going to be 0. for this whole section. And so up until basically this point right here, we know that our velocity function is going to look a little bit like this. It's just 0 in here because the slope is 0. Now, for our next section, we just figured out, we looked at this one right here, at this part right here, that basically this has a slope of negative 0.5 meters per second. So what does that mean? Well, it means that we're going to have a slope of negative 0.5 on our next one here. Now, the only question we're going to run into is that how will these always fit? Because we have to get our scale. We have not set up a scale for our velocity over here yet. 0 is pretty straightforward. Didn't have to really do anything on that, but we do need a scale here. To find our scale, we want to find what's our maximum velocity. And to find the velocity, you need to look at what is the largest acceleration we have here. Well, look at the slopes. We have, this section there, and we have this section down here. That's pretty negative. Then we have our curve section here, which has a really high slope at the very end. The one we just figured out at the very end there, where we said that that slope here, where it rose by 3 and went over by 1, and so that would be a slope of 3. So we know we're going to have to at least go up to 3 on that side of things. On the negative side, looking at this section that goes right in there, that we went from 2 over here at this point right there, all the way down to this point right here, which is at negative 4. So it dropped by 6, divided by the time between 7 seconds and 13 seconds. So that's a matter of 6. So that's negative 1. So we know that basically our lowest value has to be negative 1. Our highest value has to be positive 3. And so let's just do it this way. Let's say that make sure I can think of the right scale here. Yep, we'll say every 8 boxes is 1. And so to do our scale right here, we would say that this is going to be 1 meter per second. The next one would be right here, would be 2 meters per second. And then the next one right up here would be 3 meters per second. And the same thing sort of down for the negative side, that we have negative 1 right there. We have negative 2 right there for our units, meters per second still. So this we have, and obviously 0 is sort of right in the middle. All right, so for our next section, we are at negative 0.5. And so if we were to sketch that out, we would say that negative 0.5 would be right about in here. And it's going to go until we reach to 7 seconds. And so at 7 seconds, it's going to quit right in here. And so this right here would be our next section on our velocity graph right here. Now, for our next section here, we find the slope. We said the slope, it's going from, basically, we said from 2 all the way down to negative 4. And so that's 6 seconds, or 6 meters, negative 6 meters that it drops by. And then the run, it goes from 7 seconds over to 13 seconds. That's 6. So negative 6 divided by 6 is negative 1. So it means that between 7 seconds and 13 seconds, the slope is going to be negative 1. And so here's our slope down here, negative 1, going all the way over to 13 seconds. If I could draw straight once again. So that's basically what we're going to get right there. On our last section, though, we have a curve. And so the slope is changing over this period. On the first section, sort of right in here, looks like the slope is actually between, if we look sort of very, very carefully on this curve, the slope looks like it's basically 0 in there. And so what we can say is that this slope starts off at 0, because that first section we know is at 0 here. Now, to make this sort of work out, what we're going to do is we're going to pick the midpoint here. And so we know halfway between 13 and 14 that the slope is going to be 0 right here. That's what we've got there, because that's what we can see. Halfway between this point and this point, the slope is basically flat. And so we'll say that's 0 here. On the last section, basically, we're at 19.5 seconds. It's going to be halfway between this point and this point. We already found out there that the slope is going to be 3 for that, because we said it rises up from, I think we said it's going to be 3. It rises up from 3 to 6 in 1 second. And so the rise is 3. The run is 1. 3 over 1 is going to be 3. And so this has a slope of 3 in here. And so at the point that's basically halfway between these 2 points, which is 19.5 seconds, we're going to say that the slope is 3. And so we have this right here. Now, if your curve that you have on your graph is a parabola, whenever you basically take the slope of that parabola, you're going to end up with a straight line. Those of you who are basically in calculus, who have taken some calculus, know that if you have a parabola, which is a quadratic function, and you take the derivative of that, you're going to get basically a linear function. You get something that's to the first power. We sort of saw a little bit of that last time. And so in this case, this graph is going to have to be, for this section, basically a flat line that goes along here. And I'll tell you this, for this class, anytime I give you a curve, it is going to be a quadratic function. It's going to be a parabola here. And so this is what we end up with for our graph so far. This is our graph of the velocity. And so we now have a velocity versus time graph. That's in our red. And so to find our distances, we want to find our areas. And so the first question is, what is the distance at 5 seconds? Well, the first section here is basically right in here. That's got to have an area, it's going to have a slope. We're trying to go from a velocity versus time graph to acceleration versus time graph, so we have to look at the slope. And so ignore those areas right there. That should not be there. I was going the wrong direction. Didn't give us a good value there. So the slope right here, basically at 5 seconds, which is going to be this point right here, has a slope of 0. And so basically the acceleration of this graph right here at 5 seconds is going to be 0 meters per second, because you can see the speed's not changing. It's pretty level from in here. It's not changing at all. At 20 seconds though, 20 seconds right up here, this graph is changing here. This is rising, and it rose from 0 at 13.5 seconds up to basically 3 at 19.5 seconds. That's the one that's right up here. And so we have a rise of 3 divided by a run of from 13 to 19.5. That's 6 seconds. So 3 divided by 6 here, and so we get 1/2. And so basically what we get here is the acceleration is 0.5 meters per second squared. And so that right there is how you'd go about figuring these out. So you have an acceleration versus time graph, a distance versus time graph that we started off here. You first want to find the slopes of that to generate a velocity versus time graph. Once you found the velocity versus time graph, you basically find the slopes of those to find the distance versus time. And that's basically how you go about setting these up.